The world's oceans are not merely water, they are the primary circulatory system of the global economy. 90% of all international trade travels by sea, passing through a handful of vulnerable strategic choke points. To control these waters is to control the destiny of nations, a reality the United States Navy has enforced for decades. But the era of uncontested American naval dominance is evaporating in the face of next-generation warfare. Hypersonic anti-ship missiles and satellite-guided ballistic killers have turned the open ocean into a high-stakes kill box. A floating airfield costing $13 billion is no longer just a capital ship. It is a massive, high-value target. Yet, the necessity of air power at sea remains absolute. Static airbases are fixed, targetable, and politically constrained. The solution is not to retreat, but to evolve the aircraft carrier into a platform of unprecedented kinetic density. Enter the Ford class, the most technologically complex warship ever conceived by human engineering. This is not simply an upgrade to the legendary Nimitz class. It is a total reimagining of naval aviation physics. At 100,000 tons, USS Gerald R. Ford is a sovereign piece of American territory capable of 30 knots. Its mission is simple: project overwhelming force, sustain it indefinitely, and survive in a contested electromagnetic spectrum. The design philosophy centers on a single, ruthless metric known as the sortie generation rate, or SGR. In modern combat, the side that puts the most ordnance on target in the shortest window wins. The Ford is engineered to launch 160 aircraft missions per day, surging to 270 in crisis. This represents a 30% increase in lethality compared to its predecessor, a margin that defines victory or defeat. Achieving this required stripping the ship down to its frame and rebuilding the concept of energy management. The beating heart of this Leviathan is a pair of Bechtel A-1B nuclear reactors, significantly smaller than previous designs. Despite their compact size, they generate 25% more thermal energy than the A-4W reactors of the Nimitz. But thermal output is only part of the equation. The real revolution lies in electrical generation capacity. A Nimitz-class carrier generates enough electricity to power a small town. The Ford generates enough to power a city. With 3 times the electrical generation capacity, the A-1B reactors future-proof the hull for directed energy weapons. This massive surplus of electrons is essential because the Ford has abandoned steam for the precision of electromagnetism. Traditional carriers rely on high-pressure steam pipes running through the ship to power catapults, a maintenance nightmare. The Ford replaces this antiquated plumbing with the Electromagnetic Aircraft Launch System, or EMALS. EMALS uses stored kinetic energy to accelerate aircraft with digital precision, reducing stress on airframes. It allows the ship to launch heavy strike fighters and lightweight unmanned drones from the same catapult without adjustment. The system draws power from the ship's grid, stores it in massive flywheels, and dumps it in a 3-second pulse. This energy dump propels a 30-ton aircraft from 0 to 150 miles per hour in less than 300 feet. But launching aircraft is only half of the physics problem. Recovering them requires dissipating massive amounts of kinetic energy. The Advanced Arresting Gear, or AAG, utilizes water twisters and electric motors to catch incoming jets. Unlike hydraulic cables, the AAG can be instantly recalibrated by software to match the weight of the incoming aircraft. This allows the Ford to recover a wider range of aircraft types, from heavy tankers to fragile reconnaissance drones. The integration of these systems reduced the crew requirement by nearly 1,000 sailors, lowering lifetime operating costs. Automation handles weapons transport, moving ordnance from deep magazines to the flight deck with linear motor elevators. These advanced weapons elevators move 24,000 pounds of bombs at 150 feet per minute. Faster rearming means faster launches, directly feeding the sortie generation rate and keeping the enemy under pressure. The flight deck itself was redesigned, moving the island superstructure aft to create more usable tarmac for pit crews. This pit stop concept allows aircraft to land, refuel, rearm, and launch in a fraction of the time required on the Nimitz. Every square foot of the 4.5-acre deck is optimized for the rapid cycling of war machines. However, birthing this new class has been a painful process, plagued by cost overruns and technical failures. The dual-band radar system, designed to track threats and guide missiles, proved so expensive it was cut from future ships. Early trials of the magnetic elevators saw them failing to operate, leaving ordnance stranded in the bowels of the ship. Critics argued the Navy tried to introduce too many immature technologies into a single hull simultaneously. Yet, the strategic calculus remains. Without the Ford, the U.S. Navy cannot maintain superiority in the Pacific. China's naval modernization is producing carriers and escort cruisers at a rate that alarms Pentagon planners. To counter this, the Ford must work not just as a ship, but as the central node of a distributed kill web. It connects with submarines, satellites, and unmanned wingmen to create a sphere of denial around the strike group. The sheer scale of the engineering effort is visible in the construction of the second ship, the John F. Kennedy. Using superlifts, engineers assemble the hull in massive blocks, dropping 1,000-ton sections into place with millimeter precision. The assembly of a Ford-class carrier is less about shipbuilding and more about modular industrial integration on a planetary scale. Construction does not happen in a single dry dock. It begins in steel shops scattered across the shipyard. Engineers fabricate massive independent sections known as superlifts, complete with cabling, piping, and ventilation pre-installed. These modules can weigh over 1,000 metric tons, pushing the limits of terrestrial lifting capacity. Moving them requires Big Blue, the largest gantry crane in the Western Hemisphere, a machine capable of lifting 1,050 tons. This crane operates with surgical precision, aligning steel behemoths to within a fraction of an inch. The process turns the ship into a three-dimensional jigsaw puzzle, where every piece must fuse perfectly to ensure structural integrity. Once welded, these sections form a hull that is as tall as a 24-story building and as long as the Empire State Building. Inside this steel skin, a labyrinth of systems must support a crew of 4,500 personnel. It is a closed-loop ecosystem, processing sewage, desalination, and 20,000 meals a day without external support. But comfort is secondary. The ship's internal volume is ruthlessly optimized for the storage and movement of violence. The hangar bay is the garage, but the flight deck is the factory floor where the product air power is delivered. On previous carriers, the island command tower sat closer to the midship, creating a bottleneck for aircraft movement. Naval architects for the Ford analyzed decades of deck logs and identified this placement as a critical inefficiency. They made the radical decision to slide the entire island structure 140 feet toward the stern. This shift opened up acres of usable deck space forward of the tower, creating a dedicated pit lane for aircraft. Jets can now land, taxi to the refueling pits, rearm, and move to the catapults without crossing paths. This unblocks the flow of traffic, removing the foul deck situations that plagued Nimitz-class operations. The island itself was redesigned, shrinking its footprint to grant even more real estate to the flight deck. Inside the tower, flat panel arrays replaced rotating radar dishes, reducing maintenance and electromagnetic signatures. Yet, the most enduring feature of the deck is a geometry inherited from the Cold War, the angled runway. In the dawn of the jet age, carriers utilized straight decks, a design legacy from World War II propeller planes. As jets became heavier and faster, landing them on a straight deck while others launched became a mathematical impossibility. If a pilot missed the arresting wire on a straight deck, there was nothing ahead but parked aircraft and a fatal collision. This inefficiency forced commanders to halt all launches while recovering aircraft, paralyzed by the geometry of the ship. The solution came from British engineers in the 1950s, who simply angled the landing strip 10 degrees to the left. This angled deck allowed a bolting aircraft, one that missed the wire, to accelerate safely back into the air. It decoupled launching and landing operations, allowing them to occur simultaneously and continuously. The Ford class refines this geometry, widening the runway to accommodate the wingspans of future unmanned combat vehicles. Every degree of angle and foot of width is calculated to maximize the safety margin for pilots operating at the limit. Managing this flight deck is often described as controlled chaos, but that is a misnomer. It is high-stakes choreography. Handlers wear color-coded jerseys to signify roles: purple for fuel, red for ordnance, green for movement control. They communicate over the roar of jet engines, using a visual language of hand signals developed over 70 years. But on the Ford, this analog ballet is augmented by digital tracking systems embedded in the deck itself. Logistics software tracks the position of every fuel hose, bomb cart, and tow tractor in real time. This data feeds into the flight deck control center, allowing the handler to play Tetris with billion-dollar assets. The goal is to minimize the cycle time, the minutes it takes to turn a landed jet back into a weapon. A reduction of just 5 minutes per cycle accumulates into dozens of extra sorties over a 24-hour combat period. This tempo places immense strain on the human components of the system, the pilots and deck crew. To mitigate fatigue, the ship utilizes automated logistics to bring weapons to the flight deck faster and safer. The advanced weapons elevators eliminate the human chain of handling, moving ordnance directly from the magazine to the waiting jet. These elevators are electromagnetic, utilizing the same linear motor technology as the launch catapults. They travel through trunk lines that are sealed against blast and fire, preserving the ship's survivability. If the hangar bay takes a missile hit, the magazine remains isolated behind heavy blast doors. This compartmentalization is critical because the Ford is designed to fight while hurt. In a peer conflict, the carrier will not operate with impunity. It will be hunted by satellite constellations and submarine wolf packs. Damage control systems are automated to isolate flooding and fire instantly, keeping the flight deck operational. The ship's survival depends on its ability to launch the air wing before the enemy's kill chain can close. Speed is armor. The faster the Ford moves and launches, the harder it is for ballistic missiles to calculate a solution. But speed requires power, and the engineering challenge of propulsion is where the nuclear advantage becomes absolute. Diesel-powered carriers are tethered to a logistical umbilical cord. They must refuel every few days or become dead in the water. The Ford breaks this dependency entirely, carrying enough nuclear fuel to circle the globe for 25 years without stopping. This strategic autonomy is derived from the A-1B reactor, a marvel of thermal engineering that is deceptively simple in concept. Uranium atoms are split, releasing heat that boils water into high-pressure steam. This steam drives 4 massive turbines, which in turn spin the 4 propeller shafts, pushing the ship through the water. But unlike its predecessors, the Ford diverts a massive portion of this steam energy into electrical generation. It is essentially a floating power plant with an output of 600 megawatts, 3 times that of the Nimitz. This electrical surplus is the lifeblood of the ship's most critical offensive system, the electromagnetic catapult. For 60 years, steam catapults were the gold standard, brutal machines that punched aircraft off the deck. They worked, but they were violent, imprecise, and notoriously difficult to maintain. Steam systems have no feedback loop. Once the valve opens, the energy release is uncontrolled and linear. This sledgehammer approach places immense structural stress on the airframes of delicate fighter jets. The Ford's EMAL system replaces the sledgehammer with a digital railgun. A linear induction motor creates a traveling magnetic wave that pulls the aircraft down the track. Crucially, the system monitors the launch in real time, adjusting the magnetic force thousands of times a second. If the system detects a flutter or an anomaly, it can tweak the acceleration profile instantly to protect the aircraft. This smart launch capability extends the lifespan of the airwing, saving billions in maintenance costs over the ship's life. More importantly, it allows the Ford to launch the future of naval warfare, swarms of lightweight, unmanned drones. A steam catapult would rip the wings off a light drone. EMALs can accelerate it with the gentleness of a luxury car. Conversely, it can dial up the power to launch a fully loaded bomber at maximum takeoff weight. This flexibility turns the Ford into a universal socket for any aircraft the Pentagon designs for the next half-century. However, the transition to electromagnetics has not been without significant teething problems. Early tests revealed a software flaw that caused excessive vibration during the launch of aircraft with external fuel tanks. The system also suffered from a poor mean time between critical failures, breaking down far too often for combat reliability. Critics pounced, calling EMALs a science project that jeopardized the readiness of the fleet. But engineering is an iterative process. Software patches and hardware hardening have steadily improved reliability rates. The launch is only the beginning. The aircraft must return. And here, physics presents a terrifying challenge. A pilot must land a 20-ton jet moving at 150 miles per hour on a pitching deck in the middle of the ocean. Historically, this was achieved with a hydraulic arresting engine, essentially a giant piston that absorbed the shock. Like steam catapults, hydraulic arresters are dumb systems. They are set for a specific weight and cannot adjust mid-landing. The Ford's Advanced Arresting Gear, or AAG, digitizes this process using water twisters and electric motors. As the tail hook grabs the wire, the system measures the energy of the aircraft and applies the precise amount of resistance needed. It is a smart catch, reducing the peak loads on the hook and the airframe. This system, too, faced a rocky development path, with early failures casting doubt on the entire program. Yet, the ability to recover lightweight drones alongside heavy fighters is a capability no other nation possesses. The combination of Naval's and AALO's, the Ford to operate a mixed air wing of unparalleled diversity. But the ship itself is just a host. The real teeth of the carrier are the aircraft it projects. The current air wing is dominated by the F-35C Lightning II, a stealth fighter that acts as a sensor node. The F-35 does not just drop bombs, it vacuums up electronic data, building a picture of the battlefield for the entire fleet. Yet, even the F-35 has limitations, specifically in range and payload capacity. To overcome gravity and drag, these jets rely on afterburners, a technology born from the desperate innovation of World War II. Sir Frank Whittle's invention dumps raw fuel into the exhaust stream, igniting it to create a massive spike in thrust. This allows a heavy jet to get off the deck safely, but it consumes fuel at a catastrophic rate. Managing this fuel burn is a critical tactical decision for the air boss in the tower. Every gallon of fuel burned on takeoff is a gallon not available for the mission or the return trip. The Ford's high-efficiency launch system aims to reduce the need for afterburners, saving precious fuel for combat. This efficiency becomes vital when the carrier is operating thousands of miles from the nearest tanker. The strategic vision for the Ford is to operate inside the anti-access area denial bubbles of adversaries like China. These zones are defended by long-range missiles designed specifically to kill carriers. To survive, the Ford must launch its aircraft from outside the range of these carrier killer missiles. Launching an aircraft is a test of power. Landing one is a test of structural violence. To recover a jet, the carrier must dissipate millions of foot-pounds of kinetic energy in 2 seconds. If the arresting system fails, the aircraft is not merely stopped, it is destroyed, and the pilot is lost. This engineering problem was first solved in 1911 by a daredevil pilot named Eugene Ely and a brilliant engineer, Hugh Robinson. Ely flew a Curtiss pusher biplane onto the deck of the USS Pennsylvania, a modified armored cruiser. He had less than 120 feet of runway, a distance that guaranteed disaster without external braking. Robinson's solution was elegant in its simplicity. A series of ropes strung across the deck, weighed down by sandbags. Hooks on the biplane's undercarriage caught the ropes, and the drag of the sandbags absorbed the plane's momentum. It was the first crude application of the tailhook concept, a mechanism that remains the gold standard of naval aviation. The physics remain unchanged, but the variables have scaled exponentially. Ely's biplane weighed roughly 1,000 pounds and approached at 40 miles per hour. An F-35C weighs up to 60,000 pounds and slams onto the deck at 150 miles per hour. The kinetic energy involved has increased by a factor of nearly 2,000. A sandbag system will be vaporized. Even traditional hydraulic pistons are pushed to their thermal limits. This is why the Ford's advanced arresting gear is not a luxury, but a thermodynamic necessity. The water twisters inside the AAG absorb 70% of the impact energy, converting it into heat within the fluid. The remaining 30% is handled by electric motors that act as regenerative brakes, dumping power back into the ship's grid. This system allows for a soft catch, reducing the G-forces transferred to the airframe and the pilot's spine. But proving these technologies on the lead ship, the Gerald R. Ford, was a trial by fire. The Navy is now applying the hard-won lessons of the Ford to the second ship of the class, the John F. Kennedy. Currently nearing completion in Newport News, CVN 79 represents the first iteration of the class's maturity. Engineers have modified the build strategy, constructing the Kennedy with larger and more complete superlifts. By installing more electrical cabling and piping before the hull sections are joined, they have reduced labor hours significantly. The Kennedy is expected to require 18% fewer man-hours to build than before. This efficiency is critical, as the Navy plans to build a fleet of 10 Ford-class carriers to replace the aging Nimitz ships. The strategic goal is to maintain a continuous presence of nuclear-powered airfields in the Pacific, Atlantic, and Indian Oceans. However, the timeline is tight. The Nimitz-class hulls are reaching the end of their 50-year service lives. Delaying the Kennedy would create a carrier gap, a period where the U.S. Navy cannot meet global combatant commander requests. To accelerate the timeline, the shipyard is utilizing digital twin technology. Every pipe, valve, and bulkhead of the Kennedy exists in a high-fidelity 3D simulation before it is fabricated in steel. This allows workers to identify clashes where a pipe might hit a cable tray months before they occur on the ship. The result is a cleaner build with fewer rework orders, a stark contrast to the chaotic construction of the prototype. But the Kennedy will face a threat environment far more hostile than the one the Ford was designed for in the early 2000s. Drone swarms, loitering munitions, and hypersonic glide vehicles are reshaping the defensive perimeter of the strike group. To counter these, the Ford-class hull allows for the rapid installation of directed energy weapons. High-power lasers and microwave emitters require massive spikes of electricity, which only the A-1B reactors can provide. A laser weapon does not run out of ammunition as long as the reactor is online. It costs dollars per shot, not millions. This economic asymmetry is vital when defending against swarms of cheap, expendable suicide drones. Firing a $2 million interceptor missile at a $5,000 drone is a bankrupting strategy. The Ford-class architecture anticipates this shift, providing the voltage and cooling capacity to weaponize life itself. Beyond the weapons, the ship is designed to be a command center for unmanned wingmen. Future air wings will likely consist of one manned fighter controlling 4 or 5 autonomous loyal wingman drones. The carrier must house, maintain, and launch these robotic fleets, requiring flexible deck management. The Ford's simplified refueling kits and electromagnetic catapults are inherently better suited for this robotic future. While the pilots of today fly the F-35, the ship is already being prepped for aircraft that have not yet been invented. This generational longevity is the core justification for the $13 billion price tag. A warship is not an iPhone. It cannot be replaced every 2 years. It must remain relevant for half a century. The steel laid down today for the Kennedy will still be patrolling the oceans in the year 2070. It will serve crews whose grandparents have not yet been born, fighting wars over resources we have not yet identified. Thus, the Ford class is more than a weapon. It is a multi-generational bet on American technological supremacy. The Ford class is often described as an all-electric ship, a radical departure from the mechanical drive systems of the past. But the genealogy of this electrical revolution traces back not to a carrier, but to a forgotten submarine in Cartagena, Spain. In 1888, Lieutenant Isaac Peral launched the world's first fully electric battery-powered submarine. While the world relied on coal and steam, Peral lined his hull with 613 lead-acid batteries. He understood a fundamental truth: silence and sustainability require electrons, not combustion. Peral's invention could only run for a few hours before its chemical energy was exhausted. The United German Ford takes Peral's electric dream and scales it to 100,000 tons of displacement. Instead of batteries, it uses the A1B reactor to generate 13,800 volts of distribution power. This massive electrical output replaces heavy hydraulic pipes and high-pressure steam lines with flexible copper cabling. It allows the ship to be reconfigured software side, routing power to new weapon systems as they are bolted to the deck. But the ship is merely the launcher. The projectile is the jet engine, a machine of exquisite violence. To understand the forces the deck must contain, one must look inside the hush house at Pax River Naval Air Station. Here, engineers strap down engines like the General Electric J-85 for maximum power runs. In the controlled environment of the test cell, the raw physics of the afterburner are laid bare. When the throttle hits 100%, fuel is dumped directly into the exhaust stream. The result is a controlled explosion, a cone of blue fire that generates the thrust necessary for carrier operations. On the flight deck, this heat is not contained in a concrete bunker. It is unleashed feet away from fuel lines and personnel. The jet blast deflectors, JBDs, behind the catapults must withstand thousands of degrees of thermal shock every minute. If the JBD fails, the exhaust would incinerate the aircraft waiting in line and the deck crew behind them. This is the daily reality of the purple shirts, the fuel handlers who pump volatile JP5 jet fuel into our aircraft. The logistics of fuel are matched only by the logistics of flesh and blood. The Ford is a floating city, with a population density rivaling Mumbai or Manhattan. 4,500 sailors live in a steel honeycomb, sleeping in racks stacked 3 high. Sustainment is an industrial operation. The galleys serve 20,000 meals every single day. A failure in the food supply chain or the sewage treatment plant can cripple the ship as effectively as a torpedo. Morale is a maintenance metric. The ship houses gyms, a post office, and even a Starbucks-style coffee shop. These amenities are not luxuries. They are psychological armoring for a crew that may not see land for months. The psychological strain is highest during blue water ops, where the nearest diversion airport is 1,000 miles away. Here, the pilots face the night terror, landing on a pitching deck in absolute darkness. The Ford's advanced lighting systems and precision landing modes are designed to mitigate this sensory deprivation. But technology cannot remove the fear. It can only widen the margin of error. During sea trials, the crew deliberately pushes the ship to its breaking point to find where those margins lie. They perform high-speed turns, banking the 100,000-ton hull until the flight deck is angled like a roof. They conduct dead load testing, firing weighted sleds into the ocean to calibrate the EMAL's catapults. These orange sleds, weighing up to 80,000 pounds, simulate the mass of fully loaded bombers. It was during these trials that the engineers discovered the critical importance of the software handshake. If the catapult's computer loses contact with the ship's grid for a millisecond, the launch aborts. In a steam system, physics takes over. In a digital system, code is the single point of failure. This reliability struggle is the cost of admission for the digital age. The Navy has spent years debugging the Ford, turning it from a prototype into a combat-ready asset. The result is a ship that is pound for pound the fastest and most lethal carrier ever built. Its top speed is classified, officially listed as 30+ knots, but rumors suggest it can outrun its own escorts. This speed allows the Ford to generate its own wind over deck, launching aircraft even on calm days. It also grants the strike group the initiative, allowing it to reposition 600 miles in a 24-hour period. This mobility makes the carrier a fleeting target, hard to fix and hard to hit. While satellites can track its wake, hitting a maneuvering airfield moving at highway speeds is a ballistic nightmare. The Ford's defenses are layered: interceptor missiles, radar jamming electronic warfare suites, and the close-in weapon system, CIWS. The CIWS, nicknamed R2D2, is the last line of defense, a Gatling gun firing 4,500 rounds per minute. It creates a wall of tungsten capable of shredding incoming cruise missiles seconds before impact. Yet, the best defense is the offensive reach of the air wing, striking the enemy before they can launch. In the calculus of great power competition, the Ford class is a geopolitical statement made in steel. Critics often argue that aircraft carriers are the battleships of the 21st century, obsolete, expensive, and vulnerable. They point to the proliferation of hypersonic missiles that can strike a moving target from 2,000 miles away. But this analysis fails to account for the unique diplomatic utility of a floating airfield. A missile can only destroy. It cannot patrol shipping lanes, deter pirates, or deliver disaster relief. An aircraft carrier provides a spectrum of options between a strong and a nuclear strike. It can park off the coast of a rogue nation and simply exist, a silent reminder of the consequences of aggression. This presence operations capability is why every rising power, from China to India, is frantically building their own carriers. They understand that to be a global superpower, you must be able to project influence beyond your own borders. The United States Navy remains the only force capable of deploying supercarriers in multiple theaters simultaneously. The Ford ensures this dominance continues, replacing the aging Nimitz hulls one by one over the next 3 decades. But the cost of this dominance is staggering. The total program cost for 10 ships will exceed $120 billion. Is it worth it? The answer lies in the value of the global trade system the Navy protects. Trillions of dollars in goods flow through the Strait of Malacca, the Suez Canal, and the Strait of Hormuz annually. The U.S. Navy acts as the guarantor of this free trade, suppressing instability that could crash the global economy. In this context, $13 billion for a 50-year asset is an insurance premium, not a luxury expense. Furthermore, the Ford is designed to evolve. Its architecture is open, ready to accept technologies that do not yet exist. When laser weapons become viable, the Ford has the power to run them. When 6th-generation fighters arrive, the EMAL's catapults can launch them. When artificial intelligence revolutionizes command and control, the ship's fiber-optic nervous system can handle the data. It is a platform built for the unknown, a hedge against the unpredictability of the next half-century. The engineers at Newport News have not just built a ship, they have built a timeline. From the keel laying of the Gerald R. Ford to the decommissioning of the final ship in the class, this project spans a century. It connects the industrial might of the 20th century with the digital warfare of the 22nd. Inside the hull, the spirit of innovation lives in the fusion of old physics and new code. It lives in the water twisters that catch the planes and the split atoms that drive the screws. But ultimately, the machine is nothing without the crew. Technology is a force multiplier, but the sailor is the force. It is the 19-year-old on the flight deck, fighting exhaustion and danger, who makes the system work. It is the reactor technician monitoring the core temp, and the pilot trapping in a storm. The Ford class is a testament to their skill, a vessel worthy of their sacrifice. As the USS Gerald R. Ford cuts through the Atlantic and the Kennedy prepares to join her, a new era begins. The problems of the past, the steam, the maintenance, the limitations are being left in the wake. Ahead lies the open ocean, the contested future, and the eternal mandate of the United States Navy to preserve the freedom of the seas by any means necessary. The impossible engineering of this ship proves one undeniable fact. When American industrial power is focused on a singular goal, the result is not just a weapon. It is a masterpiece of intimidation. 4.5 acres of sovereign territory, capable of unleashing hell or delivering hope anywhere on Earth. This is the Ford class.